have the right font? Let's hope so. All right. So thank you very much for the invitation. It's a pleasure to be here. As some of you know, half of my family is Bulgarian, so it's a double pleasure to be in Sofia these days. Sonia announced my talk as Spiking at the Speed of Light. This was actually the official title, but I thought since I have the last talk, I'm going to be a bit more provocative to keep you guys awake. Let's see if I can fulfill the promise. As you can see from the logo, we are working at the interface between neuroscience and artificial intelligence. So we are trying to understand how the brain works. So on one hand, well, for maybe better therapies, understanding computation in the brain, so basic research. But on the other hand, also to potentially build more powerful, more energy efficient AI, so neuro AI. So staying in the context of AI, and since we're among physicists / mathematicians, I think it's important to define the level of abstraction at which we are working. And since I will be addressing neuro AI, let's talk about AI. The structures in the brain that we are copying are these very complicated things on the left. What AI has done, even before, ever since the approximately 50s, is to simplify these neurons to very simple models that just accumulate presynaptic activity, multiply it with some synaptic weight or a matrix, and then output it through a nonlinearity. In slightly more complex models that we are mainly working with, you have a little bit more dynamics. Federico also mentioned it. We also heard it in Marco's talk, leaky integration and spiking. So these are, but it's still point neuron models mostly. One other, let's say, layer of abstraction where AI has been inspired by biology is, this is an example, is with convolutions. So we know that neurons in the visual hierarchy have receptive fields, limited receptive fields. And people in image processing thought, oh, it might be an interesting idea to take these receptive fields and copy them. And this is how then individual neurons can extract certain features, microscopic features in the image, and then pass them forward, and these features grow larger and larger until at the very top you recognize the entire image, okay? This is already for us one step too far, because these convolutions assume that each neuron has the same presynaptic weight matrix. So there is an element of non-locality here that we do not like to have, right? So our level of abstraction from the brain to AI is somewhere in between these levels, but we don't want to go this far. This is why Federico also stressed locality so much. Locality is essential in all of our work. And a place that we definitely do not want to go is attention. The most modern architectures, transformers, have this attention mechanism. I would say that this is a vague inspiration from biology, because the kind of computations, the key value query operations that happen in a transformer are only loosely based on the attention mechanisms in the brain. Okay, so now having discussed the abstraction aspects of our work, I'd like to also address hardware. And Marcos already mentioned that there is an important incentive to improve the hardware that we are currently using for neuron-like computation. What we currently have right now is a state of the art, whether we are talking about GPUs or TPUs that Google is using, are special purpose calculators that are very good at doing this one particular operation that I mentioned before. So taking an input, multiplying it with a weight matrix, adding a bias, performing a nonlinear operation on it. So this kind of vector matrix multiplication plus nonlinearity. The calculators part is essential here. So these are numerical calculators. They just calculate the outcome of particular equations. I would argue that there is a more efficient way of doing things, which I would call, and many people would call, physical computation. So as an example, let's consider the multiplication of two numbers. And on the top here, you see the digital circuit required to multiply two 3-bit numbers. It looks relatively complicated. it is relatively complicated. Now consider an alternative system where you just have a resistor and pass a current through it. If you simply measure the voltage across the resistor, this is the result of the multiplication of the current with the resistance, right? So this would be maybe the most simple instantiation of physical computation. You choose a system whose physics implements the maths that you care about. And this is what particular types of neuromorphic computing are all about, having analog systems that are capable of carrying out the mathematics, of behaving according to the dynamical equations of the models that we're interested in. And this is just one example of a chip developed in Heidelberg. I will mention it a bit later in my talk again, but what you see here are membrane potentials of individual neurons. And these are actual analog quantities on small capacitors on this hardware. And you see also that this model is not quite what you would expect from spiking neurons, where you have this Hodgkin-Huxley spike and then the refractory period. Here you just, when you cross the threshold, you just have a reset and then the neuron does whatever it does, okay? So this is the level of abstraction that I mean. You don't have to take everything from biology in order to replicate the function that biological neurons replicate. Maybe, the whole overshoot of the Hodgkin-Huxley spike is only necessary because of the biological metabolic details that we have in the brain that we do not have to necessarily replicate in chips. Okay, so having talked about biology and electronics, let's consider the carriers of information in these systems. In biology, you would have ions. This is a sodium ion. Not quite to scale, an electron. This is the carrier of information in, well, electronic systems. And now going back to the title of the talk, we would suggest that there is an even more efficient way to convey information with something even smaller and potentially faster, which is a photon. At this point, by the way, I made a simplification when I assumed that photons are necessarily faster than electrons, and any physicist in the audience who finds out what the problem is, please let me know during the talk. But if you don't find out, we can discuss this over dinner. So let's talk about photons, and in particular, let's talk about lasers. Again, with apologies to the physicists in the audience, I'm going to oversimplify how a laser works. But just as a reminder, the core component of a laser is a system composed of, it's an ensemble of microscopic systems, for example, pairs of electrons and holes in a semiconductor that can be excited. So each of these microscopic components can go from a lower level of energy to a higher energy level. And now, if you have a photon that happens to pass by one of these excited systems, what happens is stimulated emission of radiation. So if the energy difference between the two levels is correct, corresponds to the energy of the photon, then this photon will create another photon as it passes by, and the system goes back into its lower energy level. So it decays. And now these two photons are going to create 4 photons, etc. So you have a cascade. And ultimately, this is when the system is lasing, you have a mirror over here and a semi-transparent mirror over here. You have the photons going back and forth, creating more and more photons. And the output here is a coherent beam of light. Okay. Now, what happens if you add an absorber to this lasing system? So here we look at the density or number of electrons in the gain section. So this is the part that is lasing, and the number of electrons in the absorber. As we increase the stimulus, so imagine that there's a capacitor across this semiconductor laser. So you're using a current effectively to pump the laser. You're going to create more and more photons here. So you're going to reduce the number of electrons because they become photons, so to speak. However, they're going to be absorbed in this part. So this is like a sub-threshold excitation of a neuron. And now, as you excite more and more, you're going to have more and more photons here, so less electrons. And you're going to excite more and more electrons on the on the absorber side, until at some point, everything will be excited over here. The absorber will become transparent, and now the laser can laser. So you start out with sub-threshold excitations until you reach a certain threshold, and then your laser is going to spike. And this is when it emits a light pulse. At some point, all of these electron-hole pairs will be depleted. They will have recombined. And then the laser cannot laser anymore. It needs a bit of time to recover, so for the electrons and holes to be separated again. And this is equivalent to the refractory period in a Hodgkin-Huxley neuron. And then the whole thing can start over again. I will move on to this slide first. So as a small summary, in these lasers paired with absorbers, there is a thing called, a quantity called the gain. It has something to do with the number of electrons that corresponds to the membrane potential in a Hodgkin-Huxley neuron. The absorber is the leak. The pumping, you can create more or less electron hole pairs. This corresponds to PSPs. The stimulated emission, so the lasing itself, is the sodium spike. The depletion of the laser corresponds to the closing of the sodium channels and the refractoriness caused by potassium. And now, the most important part. Okay, this was to draw your attention to the most important part. The specific time constant here is on the scale of nanoseconds. So this is 6 orders of magnitude faster than the neurons in our brains. So what we can do with these systems, I'll address in a moment. But the next important thing is we only have individual neurons for now. Now we want to connect them. So you want to create an optical chip where these neurons are connected via synapses. I'll address the synapses in a moment, but first, what happens when a light pulse, a laser pulse, comes into a neuron? So I'm talking about this part over here. It activates a pair of photodiodes. So the excitatory pulse will open a diode going to a high potential. An inhibitory pulse will open a diode going to a low potential. And this is how, with every pulse of light, depending on how it is directed, it moves the membrane potential, so the gain, up or down. So it's excitatory or inhibitory. Very importantly, the shape of a PSP that you see here, so postsynaptic potential, is only an average. So what the membrane of a laser actually looks like is this wiggly shape over here. This is a Langevin process, which will become important in a second. Now, the thing that is still missing is the actual synapses. And there are several ways of realizing a synapse. I'd like to talk in particular about 2 of them. Just very briefly, one is using a so-called Machtzehnder interferometer. So what happens here is this little circle here. This is a blow-up, basically, of the circle. When a beam of light is coming in, it gets split into 2 beams, which are then recombined over here. Whenever you have a reflection, the phase of a wave is shifted by half its wavelength. So now we can look at what happens at this detector over here. You have 1 reflection, 2 reflections, and on the other path, 1 reflection, 2 reflections. So the light waves arrive in sync. So the light is fully transmitted to this detector. This would be the path going this way. Now, for the other detector, you have, again, the light bouncing off once over here. And here it bounces once, twice. And now here something weird happens because you're going from a highly refractive medium to a medium with lower index of refraction. In this case, there is no phase shift. So this reflection we need to ignore, right? So you have 1 reflection here, bam, bam, 2 reflections here. So there is a shift by half a wavelength, and you have destructive interference. So this detector over here will detect nothing. This will be the pathway going down here, okay? So by default, nothing happens. But now what I can do is I can add a current or a voltage over here that changes the refractive properties of the waveguide that I have over here. Meaning that I change the phase shift, and suddenly now, this detector will detect a bit less, and a bit more light will go through this one. The sum has to be constant because of energy conservation. So suddenly I have coupling into these vertical crossbars. And this is how I can realize a synaptic connection. Another version is using, no, please tell me that this works. Oh, I spent 1 hour last night with this movie. This must work. Please, 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 please. Oh no. See, this is what happens when you're not allowed to use your laptop. Okay, let's see if I can mime what's supposed to happen here. So imagine that there's a light wave coming here, and all of these structures here are effectively waveguides. This is a waveguide, this is a waveguide, and this is a circular waveguide. And there is, in this area where the 2 waveguides are close to each other, you have so-called evanescent coupling. So you will have part of the electromagnetic field will go this way, and another part will go into this ring. This is a micro-ring resonator. And here the same thing happens, and part of it will go this way. Now you can do 2 things here. First of all, with the same mechanism that I mentioned before, you can effectively control the optical length of this resonator. So by adding a voltage, you can make the path along the circle longer or shorter from the point of view of the light. And this is a resonator, so depending on how many wavelengths fit into this ring, you can have more or less coupling between these 2 waveguides. Meaning that if every laser has a different wavelength, then I can choose which synapse is sensitive to which laser, to which wavelength. This is one thing. The other thing is that by modifying the optical distance between these 2 waveguides, I can modify how much of the light enters the resonator and how much exits the resonator, so I can modify the strength of the synapse. It's really too bad about the movie. I'll have to show it to you tomorrow then maybe. Okay, so this is ultimately what we have. We have a laser neuron whose gain is either subthreshold, this is this blue line over here, or occasionally suprathreshold, where you get these spikes. The wiggling is the essential part here. You can use these lasers if you have a very deterministic membrane potential for standard machine learning tasks. This is a different talk, but here we will focus on the fact that the membrane, laser membrane, if you will, is effectively a stochastic process. So maybe we can use it to implement statistical models. For this, we're going to take a step back and consider what the brain is supposed to learn. And arguably, the brain is not supposed to learn a fixed model of the world because we do not have complete sensory data. A lot of my sensorium is limited. For example, for at least the people in this aisle, I do not see your legs, right? This does not mean that I assume that you do not have legs, but the precise position of your legs is unknown to me. So my world model should contain several versions of you guys with legs in different positions, right? I need to have a statistical world model with some distribution over the unknown variables to me. And this is something that I'm supposed to learn, and I'll talk about learning this in a moment. Now, how would you represent a probability distribution? One would be to do it parametrically. So for example, a Gaussian, and you give the mean and variance. Another way would be through sampling. And arguably, this is what we sometimes at least do. For example, with our visual system, you can see this either as a duck looking to the left or a rabbit looking to the right. you never see the duck and the rabbit at the same time. So you go duck, 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 and at some point your perception switches, and then you see the rabbit, rabbit, and then duck, duck, right? So apparently you're sampling. Similar situation. Sorry?
I'm asking about the rabbit. I didn't see the rabbit.
You didn't see the rabbit?
Yeah, I totally didn't see that.
These are the ears. This is the eye, and this is the nose and the mouth. Now you see it? Good. What? Okay, wait. This is cool. What do you see? What do you see here? Which one? Yes, exactly. Ah. So what are you seeing?
It's like an old someone.
An old lady, the mouth, the nose, right? So this is the jaw, this is the nose. It's a young woman looking back, right? And now you hopefully can switch between the two perceptions, more or less consciously. Okay, well, if this one gave you, wait. If this one gave you a hard time, check out this one. Yeah, but in which direction does she turn? So this one it's actually quite difficult to, it's difficult to switch. So one is her turning clockwise or counterclockwise. And, yeah. I find it very difficult to switch also. This should help you. So if you focus on either this or this leg, she either goes clockwise or counterclockwise. I'll give you a few seconds to admire this. It's so good.
In the blue, yes, I see that like to the opposite side, but in the red, I still like in the regular one, I still see red.
Yeah. I think most people prefer the clockwise version. Yeah. Yes. Although so actually only one of them is correct, and you can guess why later. But yeah. Keep in mind that only one of them is actually correct. Okay, so we are sampling reality when we observe things. We are also apparently sampling reality when we're not observing anything, namely during our dreams. We're not dreaming of everything at the same time. Usually our dreams are well-defined stories, right? So it's sampled from possible realities. Okay, so this goes back to what I said at the beginning. What you're actually doing is collecting samples. You go duck, duck, rabbit, rabbit, duck, duck. You're doing some kind of Markov chain Monte Carlo sampling, more technically from this bimodal probability distribution. And the more samples you gather, the more accurate a representation of the underlying distribution you have. And this has a lot of applications in physics, in statistics. You can do pattern completion. I'll show you that later. Constraint satisfaction problems can be solved through sampling. Interestingly, you can also solve quantum problems, and I'll also mention that later, and other things. Good. Now, what does this have to do with neurons? So, in order to sample from a probability distribution, presumably over random variables, we have to define our random variables first. And we would say that when a neuron spikes, it represents something, and when it doesn't spike, it represents nothing. So it is in some way a binary code. When a neuron spikes, while it is refractory, it represents the variable 1, and otherwise, when it's freely evolving, it represents the variable 0. So just by looking at a raster plot, you can say what variable is being represented. For example, here it's 0, 0, 1. Over here it's 1, 0, 1, etc. And now we can represent the state, the membrane potential. We can write the membrane potential of each neuron as a sum not over presynaptic spikes, but over presynaptic states. So this is a standard equation, only that the Zi are these binary states. And for those of you who have been working with systems like these, this should remind you of either Hopfield networks or Boltzmann machines. For the mathematically inclined in the audience, I added this particular part because it is actually challenging to describe what the probability of a neuron to fire, or the probability of the corresponding variable to be in the state 1 is. And it turns out that you have to look at bursts, because these neurons can also burst. So the probability of it to be in a burst of a particular length, sum over burst lengths, divided by the total time. This would be the relative probability of it being in the state 1. So this makes a lot of sense. These PNs are actually complicated integrals, but you can write them down and calculate them analytically. A very important component here is this term over here. So this blue term is the distance between bursts. And this red term is something that you don't see very well over here, but within a burst, it takes the neuron, the membrane, a little bit of time to go from the reset potential to the threshold. This time is encoded by this variable. And now what happens if this time becomes very short? Then the activation function of the neuron becomes symmetric. This time becomes short when the neuron is in a so-called high conductance state, which you certainly have in the brain, especially during periods of attention. And the symmetric activation function is interesting because then you can write down the joint probability distribution over all the variables as a Boltzmann distribution. And now suddenly you can do lots of interesting things. For example, you can start training this distribution. Now, Boltzmann distributions are second order distributions. So let's forget this term over here. All you need to train are synaptic weights that govern the correlations between variables. So you have to reduce the energy. This function over here is the energy. You just do gradient descent on either the energy or the Kullback-Leibler divergence between the target and the actually encoded probability distribution. But what you get is something very simple. You get a local Hebbian rule, which just tries to get the correlations in the model to be equal to the correlations in the data. And this is just Hebbian plasticity. And now with this, you can, so none of my movies work. This is terrible. What you should be seeing here is, no, but this can't be. We have to do something. Who is responsible for this?
He told you to copy it.
Yes.
You should not edit on his own. But we don't know the I think
Yeah, it's really too bad. There are a couple of more movies coming. It's a bit weird without, I cannot mime every movie.
Maybe.
I can connect it directly to the HDMI, or what should I do? Yeah, I can switch between the two presentations, maybe. So Mina won't be able to see the movies. I apologize, but I can send Mina the slides.
If only
Uh-huh.
the online can speak this and can send her.
So should I Zoom or should I just connect HDMI? Yeah? Let me just connect to the HDMI. Look at this. Yep. Thank you. Let's see if this works. Ha! Plug and play.
I have a link in the file.
Sorry?
I have a link in the file.
the recording was.
So, enjoy the meeting.
You can just.
I agree.
No, this is not your.
I want to enjoy to the meeting.
I can switch between presentations. Yeah.
Massimo non drinkano mentre si investono di questo
The Zoom link by email.
Yeah, but I don't have Wi-Fi here.
You don't have Wi-Fi. Yeah, is open. Open this room.
Mm,
The Wi-Fi. No, there. The first guy showed me open network. The Wi-Fi connection is not there. Images.
oh, okay. How did you send me the Zoom link? How did you send me the Zoom link?
I will send you
Email.
on your email.
Yeah. Kein muss mich irgendwo anmelden.
Bist du ein Pilot?
We have to turn off your mic. No, on computer.
This one? No?
No.
No, because I'm not connected to Zoom here. Not yet.
Yet.
Yeah,
Yeah,
so
so
I'm not online.
There is one network open.
Which one?
Go and select and show me the networks.
These are networks.
It's
I-
Fala.
This one.
There is on this. The password is here, you can see.
No, it's okay.
Okay. Okay. Let's see if I can read
Hast du
it.
gekriegt?
Super.
Yes.
So,
So. Und jetzt weiter runter. Das ist
yeah, it works. I'm connecting.
Ich habe alles rausgefunden. What's the problem now? Screen?
Yeah,
Yeah,
I'm
no.
connecting to Zoom. Good. So, I'm connected to Zoom.
There.
Yep. Okay, should be shared.
But you need to connect that screen for the
Yeah,
Yeah.
by HDMI cables.
Yep.
There is a Wi-Fi.
HDMI.
Okay.
Yeah. Wow. Broke. Oh, let's see. Okay.
Green. Because
I know. Give me a second. First, I need to if the presentation works. Good. So this works. Zoom. This should work.
now what?
Go here. So this. So far, so good. Now let's get rid of this. And let's get rid of this. It's imperfect, but it will do. Okay. I should do this, I guess. Okay. Perfect. And I hope that Mina can hear me. Good. Apologies for the delay. We had experienced technical issues. This doesn't work, of course. Amazing. Okay. So this is the movie you were supposed to see. Okay. So this is the lights coupling into the resonator and coupling out of it. I hope the mental movie that you had while I was describing it looks like that.
Okay, perfect.
Excellent. Good. Those were just where they were, but the other things are videos. Okay. Okay. Aha, excellent. Good. So you can have one of these deep networks. You can train them to be, and why does this work now? You can train them to be simultaneous, generative, and discriminative models of a particular data set. So for example, you can show them a handwritten digit, and then they will classify it. But you can also not show them anything, and then they will dream of the probability distributions they have learned. In this case, it would be a probability distribution of handwritten digits. Okay, this is a spiking network model. And now we can use our nanolasers to do the exact same thing. So here we have some probability distribution over 5 binary variables. So these are just 5 spiking neurons. This is what the raster plot would look like. And I actually don't remember which is which. In, let's say, gray, you have a target distribution. In green, you have a sample distribution. The two are very close. So this is indeed a relatively accurate process. What is particularly new is that you can now do marginalization for free. So if you do not care about the full probability distribution, but rather say about the probability distribution over 2 of the 5 neurons, what you would have to do normally is integrate all possible states of all the other neurons. And this is something that explodes exponentially. But here, in this sampling framework, you just only look at those 2 neurons. So this is one of the huge advantages of sampling. You don't have to calculate anything, you just observe the things that you care about. And also the marginal calculations, well, I should say representations, are very accurate. Here's an example of Bayesian inference. So you present the model with a couple of pixels, these are the red dots over here, that are compatible with digits 0 and 3 and incompatible with digit 4. This is what the network would do if you don't show it anything. It would dream of 0s, 4s, and 3s. But here it dreams of the conditional, given these pixels, what could the digit be? And it only switches between 0 and 3. And this is an example of pattern completion, as I announced before. You present equal values of an image and let the network complete the remaining quarter. Again, I'd like to draw your attention to the time scale over here. We are talking about sub-microsecond time scale. Okay, extremely fast computation. Now, this was speed. Let's talk about quickly about power consumption. This is a back-of-the-envelope calculation that we did for a network of such several such lasers. These are typical quantities that you would get for CPUs and GPUs on the scale of hundreds of watts. One of these laser chips would only need 2 watts for the same number of neurons, with a sampling rate that is higher, but with a much smaller energy per sample. This is one advantage of optics. You don't lose photons to friction. You lose electrons to friction. This is called resisting. And this is for the Swiss people in the audience presentation. So the number of samples that you can draw for the energy available in 100 grams of Swiss cheese is 3 orders of magnitude, 2 to 3 orders of magnitude larger than what you would get for a modern GPU, right? So this is several orders of magnitude in improvement in energy consumption. Okay, now I mentioned quantum before. This will have to be short in the interest of time, but just to say that if you want to represent a quantum system, what you would have to represent is either its wave function or alternatively its density matrix. The problem with density matrices is that they have complex entries, but this is a way of transforming the density matrix to a positive operator defined values, POVM matrix, into real data matrix, and now suddenly you have real numbers normalized, and then you get a probability distribution. So you can use probability distributions to represent quantum systems. In this particular case, a bell state is famous for, in certain cases, being classically impossible to realize. And with a spiking chip, we were able to realize the representation of this bell state, also including these bands over here of the quantum regime. That is, again, it's a form of representation of information that is impossible to achieve with classical systems. Since I mentioned photons and electrons before, just a quick movie of the evolution of the accuracy of the representation. So what you have here, unfortunately, you can't read it, it's too small. This is the Kullback-Leibler divergence between the sample distribution and the target distribution. You see that at some point it reaches a low value, and it converges, let's say, roughly somewhere over here. This is on the scale in biology. It would be on the scale of 10 to the third, so 1 second. And here in the chip, it's 0.1 milliseconds, right? So 1,000 to 10,000 times faster than biology. And with lasers, you can be another 3 orders of magnitude faster. Okay, now, how much time do I have left?
12 minutes.
12 minutes. Let's jump over this. Too bad, pretty movies. And let's go to this. So, it is important for us to see the rabbit and the duck. Why? Because if the alternative to the rabbit would be a tiger, in our thought example, but we only see the rabbit, then we might not be able to pass on our digits. So it is very important for us to be able to sample from different modes in such a probability landscape. The problem is that the Hebbian learning that I mentioned before tends to deepen the trust of this landscape. So if you do a lot of Hebbian learning, you get modes with barriers that are very, very difficult to cross, right? This is called a mixing problem in machine learning, and there are various strategies to solve it. Our question was, how would biology do it? And what can we learn from this for neuromorphic systems? And for this, it helps to just take another look at the energy in a Boltzmann distribution. And the energy depends on 2 things. the synaptic weights between the neurons. This is something that I mentioned before. But there's also another parameter in physics that is the temperature. So if you have high temperature, then the system whizzes around through the landscape because all states, you can reach all states with equal probability, basically. So these are the two parameters that we can modify in order to improve the mixing properties of our spike-based sampling. And how would you modify synaptic weights non-permanently? Through short-term plasticity. So if you have short-term depression in particular, so a little bit of short-term facilitation followed by short-term depression, what you do is, with a short-term facilitation, you deepen the trough a little bit initially, so you get a, let's say, crisper image. But then, as the trough goes higher, it throws the system out of its current state and allows it to explore other states in the energy landscape or probability landscape. The other parameter we can touch is the temperature. And now, I mentioned before that the noise in the system is important, so the wiggling of the membrane potential. And you can imagine that with a higher effective temperature, so not the actual temperature in the brain, but whatever the temperature, the equivalent of the temperature is in the brain, the wiggling should increase in amplitude. Now, what determines the amplitude of the wiggling? It's the background firing rate. And what oscillates in the brain? Well, firing rates. You have oscillations in all possible bands, right? Alpha, beta, gamma, etc., depending on the frequency of the oscillation. So, cortical oscillations are a way in which nature could implement the equivalent of temperature. And when the background firing rate in the brain oscillates, what happens is that it squashes the energy function periodically. And when the energy function is flat, it allows the system to leave the local mode. Here's an example of what this would look like. Here's a, so this is a network that has learned to represent images of children's toys. This would be what the network does with a fixed low background rate. It is fixated on a particular toy, dreams of one toy only. This is what would happen if the brain had a constantly high firing rate. Then it would constantly be in a superposition of all possible toys. But if you have this oscillatory changes in the background firing rate, you can have nice switches between the different things in the system. And now, Anno would say, should say, has said that, but there's a problem, you are assuming symmetry.
Yes.
Thank you, Anno.
I mean, now I'm switching the world concept.
Exactly. So this is W over here, this is a matrix, and it's a symmetric matrix. So reciprocal connections are equal. That is a problem, we had the same problem before. So the question is, how do you solve this so-called weight transport problem? So this is the last piece of the puzzle, the missing element of beauty. And it's important in any analog system. So in digital systems, you can define all your quantities to an, in principle, arbitrary degree of precision. Occasionally, you have a cosmic ray and then the bit flips, but otherwise, everything is perfect. This actually happened. Well, I'll talk about it later. No, not now. Excellent. So, if you have an analog system, it's difficult to precisely modify the analog synaptic weights. And in particular, so that's one problem. And the other problem is, how does this synapse, as Fede mentioned before, know about the weight of this synapse? How do you transport the weight from one synapse to the other? This is a problem that appears in many situations. Fede talked about backprop before, so the matrix that backpropagates the errors should be the transpose of the matrix that propagates the activities, but also in this kind of Hebbian, wake-sleep, contrasted learning, the weights and the weight changes need to be symmetric. The problem that you have if your weights are not symmetric is that when you learn, you might go the wrong way. So if your weights are slightly asymmetric, then maybe you will not follow the precise gradient to the bottom, but you will have a gradient that has a small angle, and if you pray long enough, then you're going to spiral into the local minimum. However, if the weights are too asymmetric, then it might be that the sign of your gradient flips. And now instead of going down the energy landscape, you go up the energy landscape. So you increase the loss. You make the system be more long through your elasticity. So this is really a big problem. I'll mention one more thing, that it's not enough to define your weight changes numerically. So if you have a couple of neurons and one innervates the other at a more distal position, and the second innervates the first at a proximal position, then the effect of the two synapses will be different, even if the synapses are identical, just because PSPs get attenuated as they travel, okay? So what we care about is even worse. What we care about is not the numerical value of the synaptic weight, but actually the effective value of the synaptic weight. So the coupling between the systems, right? How much do I move in the output given the move in the input? This is what we actually care about. And as maybe many of you know, this was the main criticism level that all of these models back in the 80s, famously Francis Crick said that this is why backpropagation is nice, but the brain can't do backpropagation. Presumably he would have also disagreed with these sample weight models. Now, if we consider a pair of neurons that is noisy, so you have something like a distribution over spike timings, and you consider a system where the weights, the reciprocal weights, are equal. What would you think that the spike timing distribution, so T post minus T pre, would look like for such a system? I'll give you a couple of seconds to think about this. Those who have seen this presentation already, please don't answer. Excellent, good. So this was supposed to be the hint, but you don't need it. Exactly. So follow this dashed line over here. If the weights are equal, you have this distribution of spike timing differences. It has some shape, but it's symmetric. That's an important thing. And now, if the weight in one direction is larger, the integral has to be 1 because it's a probability distribution. You shift mass from the left-hand side, for example, to the right-hand side. So unequal weights manifest in an asymmetric distribution of spike timing difference. But the spike timing differences are available to both synapses. This means that just by looking at this distribution, every one of either of the two synapses can know what to do. And in particular, what standard SDP would do is it would shift mass indeed towards the causal branch, right? So standard SDP in principle explodes, as you know, right, in terms of weight. So you need to do the opposite. You need to have a homeostatic mechanism. If this mass is larger, shift it back, and you get this with anti-SDP. So it's SDP exactly flipped on its head. And as you know, if you ever looked at biological data about plasticity, you know that there are many, many plasticity curves. The standard BN2 98 plasticity is one of many. And there are others that are more symmetric, like a Mexican hat. And such shapes can also be observed. If you want, you can say basically whatever plasticity function you're looking for, you will find that in data. But this is a very, very simple mechanism that allows you to solve the weight transport problem. And these would be the trajectories of two weights. I don't know if this is me, but let's see. Does this help? Let's see. Okay, so we start with two weights at different positions. This mechanism makes them nicely equal. The cool thing is that you don't have to have plasticity in both synapses. it's enough that one is plastic and then it will equalize. So this is a scenario where one synapse has no plasticity. Nah, it wasn't that. The other one is anti-Hebbian, and they converge to the same value. So wherever you start in the Wij, Wji phase plane, you move towards the diagonal. I need at most 1 more minute. You can use these ideas not only in sampling networks, but also in deep networks. There are other models that also try to transport weights in deep spiking networks. We do better. So this is the angle between the forward and the backward matrices. Our model is blue. The others are not blue. So really, anti-Hebbian SDP is not just the simplest, but also the best functioning model. And if you go back to the sampling scenario, you can see how if you add noise to the synaptic weights, so if you make them asymmetric, then your Kullback-Leibler divergence will go up, so between the sampled and the target distribution, so your system will be wrong. But if you add this spike-based alignment plasticity rule, you go back to the optimal case. This also works for increasing levels of noise. So as you increase the synaptic noise, your distribution will become worse and worse, but it can perfectly be recovered by sampling. And with this, I arrived at the end. I would like to thank our sponsors, the Human Brain Project back in the day, these days eBrains, and in particular the Manfred Scherk Foundation for Brain Research, and all of you, and I'm happy to take your questions.
So we are out of time. But if you want to discuss, I can now leave my chair function and you stop whenever you want. Should we continue a little bit? Maybe 5 minutes? At most?
Good question. So your photonics examples, we know how electronics scale. And I think just noted that in your photonics examples you have like 5 euro. How does photonics scale?
Yes.
When you do the complexity?
It's a very good question, and you put your finger on the biggest problem of photonics. Scaling is the problem. So in individual chips, you can have on the scale of tens to hundreds of neurons, maybe. But if you want to go to tens of thousands or even more, you need solutions that there are some ideas today, but I cannot say that, for certain in 2 years we'll have this type of chip. Yes, scaling is the problem.
Do you have patents on this?
On the chip technology, no, because this is not ours. So our part was the theory, etc. The chip technology, I quoted a few papers. These ideas are pretty new. They've been published a few years ago. I don't know if they are patented. One would have to check. Yeah.
The delay in your like the communication, because I mean, you go through the analogy between the elements, you promise devices validate, and wait,
Yeah.
and then update on block. I think this is
Correct. Yes. The delay is given by the speed of light. Absolutely. And by the way, this is where you should have corrected me when I said the one thing, because in electronic systems, signals are also transmitted with the speed of light. Electrons are slow, but the fields are, well, 2/3, but still, right? Okay, so it's not that lasers are much faster than electrons, but it's that the lasing process itself, the thing that generates the spike and then the refractory period, that is very quick. This is what makes these systems quick, not the propagation of light. Okay, so very important thing. Right, now, having said that, the dynamics, so the membrane time constant, if you will, let me just jump back here. Okay. This thing over here, this is actually governed by an electronic system, by these photodiodes. So this is a bit slow, and this is useful, because then the delays that you have through the speed of light, the light traveling across a millimeter, is nothing compared to these time constants over here.
Yeah, makes complete sense.
Very last question by anybody?
No,
Oh, okay, then please.